This is just for fun. Okay, so welcome to the class. This is the fourth session, if I don't remember it badly. And in the last sessions, we have been seeing different ways to calculate the gain of an amplifier. In the first lessons, we first saw that we can calculate the transfer. In order to calculate the gain of an amplifier, we can calculate the whole transfer function, and then by setting the Q point, the quiescent point, we calculate the derivative of the transfer function at this point, and we get the gain. Okay, so this is complex because calculating this transfer function using the large signal model is not easy. And then the second option, which is much better, was using the long signal model just to calculate the quiescent point, and then we transformed the circuit using the small signal model. Okay, we saw how to do that. We entered into some details into the MOSFET model, and we studied how or where the small signal model comes from. Any questions about that? No? Okay, anyway, we saw that this is only for low frequency. And then the next day, we saw that this can be improved just by including some capacitances. We studied how the MOSFET model includes these capacitances, and we saw that the final model looks something like that. Okay? Yep. Yeah, do you remember all of this? Yeah, so more than 3 hours in just less than 1 minute. Yeah, okay, that's good. Questions? No? Okay. So today we will see some, using these models, the most basic amplifier configurations. Okay? So we will first remember how the two-port model for amplifiers were working, and then some characteristics of analog design. I mean, how we decide which are the characteristics we need to design for in an amplifier. We will revisit the common source amplifier, and we will see the Miller's theorem. Have you ever seen the Miller's theorem? Do you remember it? No? Anyway, we will also see the concept of transit frequency, and we will revisit the cascode amplifier. That I don't know if you have ever visited, but okay. This is probably one of the most important amplifiers. This is something that comes from basic electronics. Okay, I don't know if you remember, but what we have is that our amplifier is linear in the small signal model. Okay, so what we have here is that our amplifier is just some linear amplifier. Okay, so do you remember when we were studying electrotechnia that we were saying, okay, yeah, we have some gains and something complex. Okay, so this is exactly the same. So we have here a gain at the input that depends on the voltage at the output, and we have a gain at the output that depends on the voltage at the input. We also have some input resistance and some output resistance. Okay? Usually in electronics, this part doesn't exist. Okay, this is 0, so this is directly connected to ground. So this reverse gain, this input gain is 0. Okay, usually. There are some cases where it's not 0, but they are designed to do that. In the general case, the input gain is 0. Okay, so there is no influence on the output voltage over the input voltage. Okay, so we need to determine 3 different parameters, which are the input resistance, the output resistance, and the gain at the output. Okay, which is also called the open circuit voltage gain. because it's the gain in voltage when there is no current through this resistance. So that means an open circuit. Then we also have this input impedance and this output impedance. Okay, so for different reasons, they are all of them important. Okay, any questions? Do you remember that? I think you were studying this in FISE, or yeah, most probably in FISE or in analog electronics, but I think it was in FISE. Yeah, or not? Yeah, okay. So do you remember that? Yeah. Okay. Sorry. This is okay. So anyway, these are not the only aspects we are interested in when we are designing an amplifier. Why are we talking only about amplifiers? Because all the circuits, all the analog circuits, are in one way or another based on amplifiers. Whenever you wish to add two signals, you use an amplifier. Whenever you wish to filter your signal, you use an amplifier. Whenever you want to do anything with your signal, you use amplifiers. So everything in analog electronics is based on amplifiers. So this is why we are focusing only on amplifiers. There are some more complex circuits out there, like mixers and other and oscillators or things like that. But the most basic building block is amplifiers, and we don't have time to get into other blocks. So basic things first. So we first study amplifiers, and then if you wish to go and make your PhD or your master on microelectronics, you will get other things to study. Okay, but anyway, apart from the input-output resistances and the gain, we need other things to consider. Okay, in fact, we need to consider these 8 things. Okay, we consider the input and output impedance, clearly, and the gain. Okay, but then there are many other things that are also important. For instance, you need also your amplifier, most probably, to be fast. So you need to consider the speed of the device. You need also to consider which is the supply voltage you will be using for your design, because the supply voltage will affect, for instance, the voltage swings and also the speed. It will affect the voltage swing because you will not be able to go farther than the supply voltage when you are moving your output. If your supply voltage is 3 volts, your output signal will not be able to go farther than 3 volts. So this is also important. So other important things are linearity, because you wish your gain to be constant all through the region of interest. You don't want your gain to be 1 in one region and to be 2 in another region. You need it to be constant, the gain to be constant. Okay? You also need the noise to be below some given margins that are dependent on the application, and also you need the power dissipation to be controlled. Okay? Usually the highest the power dissipation is, the fastest your device will be. And also the input and output impedance are related with the power dissipation and also noise. The higher the power dissipation, the higher the noise. Okay, and also linearity, and so everything here is correlated. So you need to go and reach some kind of trade-off all between these 8 variables, these 8, 9, 10, maybe performance parameters. Okay, so this is not yet a science. This is still an art. So it's fun. Okay, questions? So we will see more or less how to calculate some of these parameters, so we can decide how to design the amplifier. Okay. First of all, what are we going to be designing? Okay, there are two options, obviously. We have discrete amplifiers that are built using amplifiers, many transistors, many resistors, and so on. And they are all different. You need, in order to minimize your cost, which is basically the size of the protoboard, or the board, of the circuit, you need to minimize the number of transistors you're using, the number of devices you're using, with devices that will not usually be equivalent one to the other. They don't match. This is the technical word. They don't match. That means that the characteristics are different. That means that, for instance, if you have two different operational amplifiers, the gain will be not exactly the same. Okay, if you have two transistors, the gain will not be the same, and the threshold voltage may also vary a little bit from one to another. The good thing about the discrete design is that you can choose nearly any resistor value or any discrete component value you need. And also the capacitors, you can choose whatever you wish, and you can also include inductances, which are complex to include in other kinds of circuits. Okay, so you get this kind of circuit with arbitrary values for the passive components. The other option is going for a CMOS integrated amplifier, okay, which is something like that. That would be the layout, and here you get different things. Here you get an unlimited number of transistors. Okay, you are not limited by area. In fact, area is cheap. The most expensive thing is after that doing the integrated circuit and so on. But area is cheap. If you are integrating this amplifier inside a more complex integrated circuit, then you don't even need to worry about that. So you can put any number of transistors you need. The devices, if you are careful, if you're a good designer, a good analog designer, or not good, but you are careful, you are trying to follow some very basic guidelines, you may get devices that are well matched. That means having transistors that behave very similarly. Most probably, you will not know the exact value of the parameters, but you will know that between two different transistors, they have nearly the same value. The bad thing about that is that you need to keep your resistors well below some values, because you need some range. You need to be in the range between, say, 10 and 100 kilo ohms, and the capacitors cannot be large. They can be in the order of picofarads, and be not so large. Okay, so these are the two different aspects we have when we are doing analog design. In this course, obviously, is microelectronics, so we go for the integrated option. Okay, so we will see how to play with that. Okay, but for that, we need to know how to build transistors, how to build amplifiers. And this is, by the way, this is an operational amplifier. We will see that in another session. Any questions till now? If you have any question, please don't hesitate to ask. Just raise your hand and ask. No? Okay. So, how do we design amplifiers? Okay. Do you like fantasy novels or science fiction novels? If you like fantasy books, you might remember that in the even in reality, you might remember that in the Middle Ages or in ancient ages, the matter was thought to be formed by 4 different elements that were fire, water, earth, and wind. And some people used also ether, but okay, it was composed by 4 different elements that combined. They provided all the different combinations of matter. They gave wood. You can get human beings or whatever you wish, just by combining these 4 basic elements. For analog design, it's something very similar. Okay? We can get nearly any different amplifier by just combining three different basic configurations in small signal. Okay, so the three basic configurations for the single MOSFET amplifier are the common source, the common gate, and the common drain. And the difference is that the common means which is the terminal that is connected to ground, to the virtual zero. Okay, in the common source, the source is connected to the zero in a small signal. I mean, in the common gate, it's the gate which is connected to the ground, and in the common drain, it's the drain which is connected to the ground. Okay. Yeah. Usually, we start by using the common source, and then we add the other two stages in order to improve the design. Okay, usually only this, but this has some problems as we saw, and then we will solve them by using a better amplifier with more stages. Okay, and nearly all the analog circuits can be decomposed into a combination of these three. You can think of this as a basis for constructing analog electronic circuits. Okay. Do you remember studying that in THESE or in analog? It was in THESE, I think, wasn't it? Yeah. Do you remember? Are you there? Is it? Yeah, THESE. Okay. So till now we are just remembering THESE. Okay, let's go back to the common source amplifier again. Okay, but let's do things a little bit more complex, more funny. Okay, this is just something you already know how to design because we have done it, I think, twice or thrice. Okay, yeah, just in order to calculate this amplifier, we just select the bias point, and we decide we calculate everything else, just as in the previous sessions. Okay, I will not repeat all these calculations because they are already done. Yep. Okay. So for the analysis in low frequency in AC, we get this. Okay, we get this circuit for the low frequency. But then when we go to the small signal model, we find that here there are some strange things. Okay, for instance, here at the input, this capacitance is the addition of the gate to bulk and the gate to source. And this is because here there is a connection, which is not shown, but when it's not shown, you can assume safely that it's like that, between bulk and source. Notice that this is killing the body effect. Okay, so the only gain we have is this, the transconductance. Okay, and because of that, these two capacitances are the input capacitance. The output capacitance is this capacitance here. You have also this capacitance here, and the other capacitance. Okay, so this capacitance is just this one, okay, between the drain and the bulk, okay, here. And you also have this other two. And then, sorry, it was this one. This one between gate and drain is this one, which is a feedback path. It forms a feedback path between the output and the input. Okay, so notice that this capacitance is like adding a resistor in an operational amplifier. Okay, this one here. So we have a feedback path in the amplifier. How can we solve that easily? Okay, you can go and make here, put all the full calculations and you get some result, but this is usually complex and it doesn't give you a good insight into the problem. For that, in order to get an insight on what is happening, we get something which is called Miller's theorem. Do you remember it? Have you ever seen it? Yes? No? Just out of curiosity. Are you there? No? You think no? Okay. Then Miller's theorem is a very useful theorem that the only thing that it states, and it's also very easy to prove, it's just some calculations, that when you have something like that, an input impedance, sorry, an input, a line where you have an impedance in the middle, yeah, and when you have both voltages related by a gain, okay, then in this case, you can write this circuit as two separate circuits. Okay, which is very useful. So, in this case, you get this circuit divided into two circuits that are uncorrelated. So you can treat them separately, which is wonderful. Okay? Yep. Okay, notice that when the gain is very high, this goes to 0. In fact, a negative 0, but never mind. It goes to 0. And this goes 1 over key, and this goes to an impedance which is amplified by key. Okay? When key is big, this goes to 1 over, okay, this goes to 0, and so this goes simply to the impedance. Okay? Yeah. Any questions? This is the importance of this is the simply Miller's theorem. Under these conditions, you can separate your circuit in two different circuits. Okay, so we can use this theorem in order to simplify this design. Yeah? How? Okay. We wish to apply this theorem, Miller's theorem, to this capacitor. How do we do that? Okay, we assume that the gain, this gain is more or less the gain at low frequency, when there are no capacitors. Okay, just to make a wild assumption. Okay, so in this case, the gain, as you know, is you just remove the capacitors, for low frequency, and the gain is simply the transconductance multiplied by the parallel between the output, the output resistance and the load resistance, okay, which is this one. Okay? Yep. So we calculate the gain here, and once we have the gain, we assume that this gain is more or less the gain we will be using. So we write this input capacitance, which is the addition of this one plus the Miller capacitance coming from here, which is 1 plus this, okay? This is just here, this capacitance, okay? And then the other capacitance is just 1 over this one, okay? So notice that the output capacitance, if this gain is high, this disappears. And if this gain is high, this also disappears. Okay? Yeah. So what we get is that the gain finally is calculated using this approximation, this approximate circuit constructed by using the Miller's theorem. So we separate both of them in two parts. So we calculate easily which is the output, this voltage here. This voltage here is simply a voltage divider between this capacitor, this impedance, and the gate resistance, and the source resistance. And the output is just the current multiplied by this parallel impedance. Okay? Yep. So finally, if you wish, you can do that at home. The gain is simply this one here. Okay, and you can also calculate the input impedance, the output impedance, and the gain in current. Okay, but notice that here this is very much simplified by using Miller's theorem. Otherwise, it's quite complex. Here, using Miller's theorem is quite straightforward. You only need to calculate this current here, which is this GM multiplied by this tension here, which is simply a voltage divider, and then the output is simply this multiplied by the parallel of the resistance. Okay, so it's fairly easy. Questions? Do you remember having seen this before? No? Okay. Okay, so and now you should be asking me, but okay, now we have assumed that the gain was more or less constant all through all the frequencies, and now we are saying that the gain is not constant through the frequencies. Okay, so here we assumed that the gain was a constant, and here we have used this assumption to calculate a non-constant gain. Okay? So how can we know if this approximation is correct? We don't know. If we wish to know if the approximation is correct, we have to check it by hand in each case. Okay, so how do we do that? We do that by checking the position of the poles. Okay, so we can check first as a fast check that the pole at the output is much higher than the pole at the input. Okay, or that this RC constant is much lower than this other RC constant. See, if this is correct, then okay, our approach was valid. The other option is writing this function, plotting the both diagram, and we check that the poles and zeros are all much bigger than this input pole. Okay? But then in any case, it's not important whether it's exactly working or not. Okay? The important thing is that it explains how the capacitance between the gate and the drain limits the bandwidth of high gain amplifiers at the input. Okay? Just because whether the gain is the gain at low frequency or the gain is the gain at high frequency, the theorem still stands. Okay, so the input, which is seen at the, sorry, the capacitance seen at the input is amplified by the gain, from the capacitance which exists between the gate and the drain. Okay, so this is because of Miller's theorem. It's irrelevant if this gain is the gain at a low frequency or at high frequency. The important thing is that there is a gain, and if there is a gain, then Miller's theorem applies. Okay, so we can use this theorem to explain why we are seeing a much larger capacitance at the input than the one that is physically real. Okay? Yes? Any questions? Any questions? No? Okay, yeah, here. Yeah, okay. Yeah, here we have only a small example by putting some values taken from a library, from a simulator program. And if you wish, you can do that at home, just replacing these values in the previous equations. But we get that the gain is nearly 4, with a capacitance at the input which is nearly 75 femtofarads. You notice that the capacitances are all on this order of magnitude. Okay? Yeah. And notice also that this is the input at the capacitance would be this one. Okay, the addition of these three capacitors plus this one multiplied by the gain. Okay? So this one is multiplied by the gain. So this is why 73 plus 2 is 75, plus 4 by 2, which is 4 by 2 is 8. 8 plus 75 is something like 73. Okay, so it's 74. Okay, so more or less. Yep. And the output is this plus something else caused by different things. Okay, so we check if our approach is valid by just calculating this output function. We replace all the values, and we see that in fact this first pole is much lower by an order of magnitude than the other pole. Okay, so this can be simplified. This transfer function can be simplified, at least initially, to this order. Okay? Yeah? Yes or not? Anybody there? Nobody? Okay. Nobody. Yes means that there is nobody, isn't it? Okay, and then another thing that we can calculate is the transit frequency. What's the transit frequency? Okay, in order to calculate the transit frequency, we calculate the gaining current. Okay? The gaining current is just the output current divided by the input current, which is the current at the gate. Okay? We do the calculations and using Miller theorem and so on, and we get this expression here. When our frequencies are below this expression, that means this we can take away this term, okay, that means low frequencies, we get this expression for current, for the gaining current at low frequency. Okay? So this what we look is when the gaining current is 1. Okay? When the current gain is 1. At this current gain, we get that the that happens at this frequency. Okay, which is basically the addition of the transistors, of the capacitors, divided by the transconductance. Okay, this is the transit time, and the transit frequency obviously is the opposite. Okay, so we define the transit frequency as this angular frequency over 2pi. Okay, and it's very important design for high frequency because it defines when our amplifier is stopping to work as an amplifier. Okay, it means how fast can our device be, because if the gaining current is less than 1 and you are trying to drive something with it, having a gaining current less than 1 means that it's better to feed directly than to use this amplifier. Okay? Yep. Okay. So this is an important figure of merit, this transit frequency, because we used to compare the high frequency response of different MOSFETs, in general different devices. In fact, the higher this transit frequency, the fastest will be the device we are using. Okay, so for radio frequency or for digital computing, we need very high values of transit frequency. Okay, but anyway, notice that this is just an approximation. Okay, using a model which is not valid at these frequencies. Okay? The actual value is usually limited to 1/5 of this frequency. Okay, but anyway, it provides you a correct order of magnitude for this frequency. Okay, so it more or less tells you how fast can your system be. Okay, it can be increased by increasing the transconductance. You can notice this is a small signal parameter, and depends directly on the current, okay, on the square root of the current. However, increasing the current, the bias current, increases also the power dissipation, which is not good, okay, and also increases the noise, which is also bad. You always have to get to a trade-off between all the different parameters. Okay? Anyway, here another thing which is important is that this capacitance makes the transit frequency behave like proportional to 1 over the length of the channel squared. Okay, because it depends basically on the size of the transistor. So it depends on this capacitance. So this is another advantage, a big advantage of getting smaller and smaller transistors. The smaller the transistor, the smaller the length of the channel is, so the faster the transistor will be. Okay? Anyway, notice that this expression is just an approximation for long channel devices, which means it's not true. Okay? It's just an approximation. But it provides you with the right idea, maybe some intuition on what will happen. Okay, using these examples, I mean, using these values, we get that the transit frequency is around 1 gigahertz. Do you think this is fast or this is slow? Please, some answers. Fast? Any options? Why do you think it is fast? The correct answer would be, it depends. It's fast if you're talking about, well, yeah, that's it. It's fast if you're talking about systems that are running at human speed. I mean, hundreds of hertz. If you're using it for systems that are running for radio frequency or for computers or for all other things, 900 megahertz is very slow. Okay. Moreover, notice that 900 megahertz, one-fifth of that, would be around 200 megahertz, which is not very fast. Anyway, do you know something which is working at 100 megahertz, for instance? No idea? Nah, you are kidding me. Yeah, you know. For instance, I'm telling you 94.1. Does it remind you of something? The radio, yeah, FM. Yeah, that's it. What do you know what this 94.1 means? A frequency, megahertz, that's it. 94.1 is megahertz. So FM radio is around 100 megahertz. Okay. So in this aspect, these transistors would be correct to work with FM frequency, with FM modulation, at least for the first stage. After the processing, after the LNA and the mixer, they would be okay. But 900 megahertz is not very fast. If you wish to go for Wi-Fi, for instance, do you know the frequency of Wi-Fi? Wi-Fi? What in the hell is Wi-Fi? Yep, 2.4 gigahertz or 5 gigahertz. Do you know the frequency of Bluetooth? Yep, more or less the same. Yep, that's it. Do you know why we are using this frequency? It's a free frequency, yeah. Well, free means that you don't need to have a license to use it. Yeah. And why is it free? Why is it free? Okay, let me ask you a different question. Do you have a microwave oven at home? Yeah. Do you know which is the main frequency it's using for, to work? No. Well, it's using the frequency at which water it's getting the maximum absorption. Okay, which is around 2.4 gigahertz. Okay, so curiously, we are using the free band of Wi-Fi and Bluetooth and so on, just because it's a frequency which is useless for long-range communications. Just because the vapor, the water in the atmosphere absorbs the signal so fast that it's very difficult to use it for long-range communications. So this is why it's free for short range communications. Okay? Yeah. Anyway, so if we wish to use things at these frequencies, at 2 point something gigahertz or 5 gigahertz or even higher, we need to go for other kinds of devices or for other kinds of structures or for much faster devices. By the way, your computers, do you know how big is how fast is the clock they have? Hmm? Your computers most probably have some clocks running at 3 or 1 point something, 2 gigahertz. Okay, so these transistors wouldn't be useful for this kind of digital circuits. They are correct for things that running. Yep. Yeah. Yeah. So this technology wouldn't be useful for this kind of technology. In fact, it's a quite old technology, which is 0.35 microns, and your computers most probably are using things that are on the order of maybe 10, 12, 20 nanometers. So they are a lot faster. Okay, questions? No? Okay. In any case, here you have the actual values or the actual behavior of these transistors compared with the model we are using. As you can see, okay, here we are using two different things. Here we are using the maximum possible gain, do you remember? Which is simply the transconductance multiplied by the output resistance. This is the maximum gain when we have no load. And our model says something like that. Okay, like this red dot line. And the actual values are something like this orange, brown, I don't know, this orange line, which is more or less constant, around 60. So the actual model, the model and the actual measurements are quite different. Okay, so, but anyway, we are getting more or less for when we are saturation, this region, we are getting more or less the correct values, around 60, 40, okay? But once we are here, in the other part, when we go below threshold, not this is a threshold, this more or less here, when we go below threshold, that means in the weak inversion region, notice that the model predicts a very high gain, but actually we get a gain that, okay, it increases, but it also has a maximum, okay, around 60 something. Okay, but the model and the reality are different, obviously. And the other thing is the transit frequency. The model for the transit frequency is this black line, which is the long channel model. It's linear. Is the one we were talking about. It's the gain divided by the addition of the capacitances, and this is linearly dependent. This is it's just proportional to the voltage, okay, to the overshoot voltage, overdrive voltage. So this is linear, but really this is something more like a sigmoid, which is more or less a good approximation in this range here. Okay, it's more or less good, but then notice that it differs enormously for big voltages. Okay, because the long channel model is no longer applicable, is no longer valid. Okay, and this is something that is always happening. So the models we are using to do hand calculations are not actually valid. Are only approximations to get an idea on how the different transistors relate between themselves, on how all the different variables are related between themselves. But the parameters we get can be quite different. They can provide you with a good idea on a first cut design, but then you need to refine it using simulation. Okay? Yeah. So the idea is that the models are simple models used only to provide an insight into how the circuit is working, not in order to provide the exact results, because the exact results are going to be quite different. Okay? Yeah. Okay, then let's see how the cascode amplifier works. Okay, this is the cascode amplifier. Can you recognize the different parts of the system? Yeah. Can you see them? Yeah. So notice that here, for instance, below this part, what is this part? This part is a common source amplifier. Okay, the source is connected to ground, and we are driving the amplifier through the gate. Okay? And then the second stage, this second stage is a what? Which is the terminal that is connected to ground? The gate. Yep, that's it. The signal enters through the source, and our output signal is at the drain. So the gate is used only for bias. So this part here is a common gate. Okay? Yep. So we have we want to design an amplifier, and we decide to use this scheme. We have all the different parameters, the same than before, and so we have to choose the different voltage, the different bias voltage, so that everything operates correctly. We are biasing between 3 and 0, and we wish the output voltage to be at 1.5 at the quiescent point. Okay, so just equal. Okay, do you understand that? This 1.5, this 1.5 is just 1/2 of the maximum voltage. So we are setting this point here just in the middle. Okay, so we need to select these two voltages so that this is happening. Okay, so we need how much is the bias current. So we first determine this voltage here. So this transistor is in saturation, and all this current is flowing through this transistor. And then once this is set, we also set this for the transistor to be the correct value, to have the correct value. But notice that we have a free floating variable, which is this transistor, this voltage. Okay, because we don't have any variable that is relating with our voltages and this point. Okay, so we add this other condition. Okay, we add this condition just to be able to calculate this voltage. Okay, but this condition is just to allow us calculating this, and also to provide two different swing ranges for the different transistors. Okay, so 1/3 of the variation will be here in the first transistor, and 2/3 of the total variation will be in the second transistor, in the second amplifier. Okay? Yeah? Questions? No, because this is important, okay? When you are defining a cascode amplifier, you need this additional point, okay? Yeah. So we put all these conditions here, we do all the calculations. I will not do that because you know perfectly how to do, how to proceed. And we get that these voltages are very easy to calculate, okay? 1 volt, 1 volt, so this is 1.5. So this is 1.5, 1.5 volts, and this is 1 volt. Okay? Yeah? Okay, then we calculate the small signal parameters. Okay, notice that they are the same for M and M2 for both transistors because they share the same current. Okay? And we replace the transistor, sorry, the amplifier by the small signal of each transistor. Okay? Can you see this? Can you see how we transform, we go from this configuration to this other configuration? More or less? Okay. How we go from large signal to small signal? First thing, we said, in order to go from large to small signal, we put the values of all the independent sources to 0. Okay, so that means 0 current means this is an open circuit. Okay, and 0 voltage means this is a short circuit. Okay, so N2 has the gate connected to 0. L2 has the gate connected to 0, and the drain is connected to the output voltage, which is connected only to the output resistance, which is connected also to 0. Okay? Yeah? And the other part, here, M1, is simply, sorry, is simply this part here, which is exactly the same. Okay? Yep. Any questions? Okay, yes means okay, or that there are some questions. Okay, thanks. Well, and then once we have this circuit, we just replace the different transistors by their small signal model. In this case, for low frequency. First, we start by low frequency. Okay? So just M1 goes and is replaced by this, and M2 is replaced by this. Okay? Yeah, it's easy. So we just calculate, because this is very easy. So you know how to calculate this voltage, and knowing how to calculate this voltage, which is just, okay, it's just easy to calculate. You calculate also this other voltage, and then you get that the gain is this one. Okay? Yep. This is, you can do that at home. Okay? And in fact, if you go for the long analysis, you get that for very large values of RL, of the output resistance. I mean the output resistance, the open circuit gain is amplified basically with the square of the value of the maximum gain. So if this value GM R0, remember this is the maximum gain, we saw that this GM R0 is around maybe around 50. Okay, 60. So if this is amplified with a square, we are getting, instead of 60, we are going to more than 3000, which is much higher. Okay? So this is wonderful. So we are getting a very much higher gain just by adding another transistor, which is very good. And then how we get the frequency? Okay, in order to get the frequency, we just go and replace and put all the different transistors, or sorry, all the different capacitances. Okay, and then we replace this by the Miller theorem. And what else? No, that's it. We just replace this by Miller's theorem. Okay, this should be Z at the input. That means the input impedance is much higher than the input impedance of the common source. I will fix this. Okay, so this input impedance is just by applying exactly the same, is much higher. Okay, we will see that. Now it's okay. It's nearly 4. Okay, we will see that next day if you wish. Okay. Any questions till now? Does anybody have any question? It's okay. Okay. So, did you download? Okay, let me stop the recording.